I'm going to show you an alternative way of setting out the integration by parts. We set up like in columns. First column's differentiation column, second one integration column, and then the third one is just alternating plus minus if we were to keep going. Now remember, we know it's the integral of u to v. So on that first row we write that down, u to v. That's what we're trying to find. If I integrate the v, I get v, so uv, and then if I differentiate, I get du dx. Integrate again in this column, I'd now get the integral of v dx, and I go, so minus along there. This is the idea, the pattern you form that sort of hook, if you like. And again, remember you choose, so the differentiation makes it simpler, and v, obviously something you can actually integrate. Different cases. So if you have a polynomial times an integratable function, then you differentiate the polynomial down until you get 0. I've got x cos x. Differentiate down until I get 0, and then I'll just integrate in the other column. So cos will go to sine, sine goes to minus x. I have my answer. Plus x sine x minus cos x. That's the answer. X sine x plus cos x. So x squared e to the x. Okay, differentiate down on the x squared, and then I'll just keep integrating. Well, it's just e to the x every single time. Alright, now I can just write the answer down. X squared e to the x minus 2x e to the x plus 2e to the x. There's the answer. That's nice. What about if I've got a polynomial times a non-integratable function? Then we stop when the product of the lines, so you look across the line, if that's something you can integrate, that's when I stop. Log x. Now I have to use that in the differentiation column because I don't know how to integrate log x. That's the question. The other function then is 1. So I'll keep going until a line is something I can actually integrate, and straight away I've got a line I can integrate, because 1 on x times x is 1. I can do that. Alright, let's write the answer down. Now, so we've got the x log x, but of course we have a missing term here, so I can't do the thing. So I simply go minus, remember we stopped at a line that I can integrate. Alright, then that's what I'll integrate. Minus the integral of 1, which is x. So inverse tan x, I'll differentiate and I'll look at that line. I can integrate that because I've got derivative times function. I can get it into that form. X inverse tan x, but then it'll be minus the integral of that line, which we said we can integrate, and we'll get minus a half log of 1 plus x squared. X cubed log x. Log x, 1 on x times a quarter x to the 4. I should be able to integrate that. So we've got quarter x to the 4 log x, but then minus the product of that line. So a quarter of x cubed, add 1 to the power over the power. Of course, if I wanted to, I could have done it this way and said, oh well, I'll just differentiate until I get down to the polynomial. Because you see, this second line, do I know how to integrate it? Well, I kind of do. We get x to the 4 log x minus x to the 4, but then I'm left with minus 3 times the integral of x cubed log x minus x cubed. Well, I can move that integral of x cubed log x to the left-hand side, and I've got, so I'm not suggesting that's the best way to do that one, but it would have been possible to pick it the other way around if we wanted to. Well, I've now got two things, and actually I can integrate both of them. So it's the same idea. I'm going to stop when the product of the line is integratable, or if it's simply a multiple of some other line that I've already got, usually the first line. And remember this one, e to the x cos x. Okay, let's differentiate e to the x sine x. So, alright, there's the first bit. I know I've got that. I'll go again. E to the x cos x. Hang on, I've got a multiple of the first line. So, alright, that's where I'll stop. So it'll be minus e to the x cos x, but then plus the integral of that line, which was a multiple of the first line. Move it over, divide by 2. Some other ones. So, x e to the x. Okay, polynomial. I'll differentiate it down to 0, and I can read my answer straight off. So I've got x e to the x minus e to the x. That's really good for those type of ones, where you just got a polynomial times something that you can integrate. Inverse sine x, but that gives me a line that I should be able to integrate, shouldn't I? X over the square root of 1 minus x squared. So I'll go x inverse sine x minus that integral. So let's integrate that, and we get plus root 1 minus x squared. Square root of 1 minus x squared on x squared. So the two functions, I'll write them as square root of 1 minus x squared and 1 on x squared. Is that a line? Yeah, I should be able to handle that because the x's would cancel and I've got just an inverse sine function. It's alright. So we have minus root 1 minus x squared on x, and then minus the integral, which we just said was, well, that's inverse sine. We have our answer. So it's a different way of setting out the integration by parts. It's just like a table form. Some people like it. Using Euler's formula. Remember this one? E to the iota theta is cos theta plus I sine theta. 2020, this question appeared. We want to show this result. It's one of our standard results. E to the I n theta plus e to the minus I n theta is that. But we know cosine is an even function, therefore cos of negative n theta is the same as cos n theta. Sine of negative n theta is the same as minus sine theta because it's an odd function, and we get the result. The imaginary parts end up cancelling out. Part 2 then, by expanding this expression, show this trig identity. Alright, expanding it out using our binomial theorem and tidying up those powers, we see we can group the, 4 iota theta and the minus 4 iota theta, and then the 2's as well, and then I can use that result again and I get 2 cos 4 theta plus 8 cos 2 theta, and of course we have the 6 at the end. We've got our result. Now, what has that got to do with integration? Absolutely nothing. But it then said, hence or otherwise find this. So we now have an expression for cos to the power of 4 theta. I can just simply substitute that expression in and integrate and get our answer. Let's go back to this one though. E to the x cos x. Well, what I now could say is that's the real part of the integral of e to the x cos x plus I sine x, which I can rewrite now as e to the x times e to the ix. And using our index laws, that's e to the 1 plus ix. Well, I just have to integrate this exponential. That'd be 1 on 1 plus I e to the 1 plus ix. But I just want the real part of that. And the reciprocal of 1 plus I can pull out the half e to the x. That's going to be the real part. But I just want the real part of that when I expand it all out. Yeah, it's a different way of doing it, but it's making use of Euler's formula to integrate.